So our final speaker today is Suren. He is a assistant professor jointly between the Departments of Arts, Media and Engineering, and Electrical Computer and Energy Engineering at ASU. And his research focuses on designing new types of computational cameras, systems, and visual computing algorithms that can extract and understand more information from the world around us. So with that, let's bring it home, Mike. Suren, sorry.
Thanks everyone. It's a pleasure to speak here at SensMACH and really interesting talks and work so far. I'm going to be talking about a broad area of research that my lab is focused on, and a particular problem that we've been tackling in software-defined imaging. So the starting point for a lot of this research is in mobile vision. And we all are now pretty familiar that mobile vision works, right? Like things like object recognition, the structure for motion, localization mapping, so on. We want these working on our cell phone all the time in real time. And the main bottleneck for this is energy efficiency, right? Like we have to charge our phones basically every day now based on all the applications and competing demands that are required from the battery. So researchers are starting to look at this cost, and that's primarily what TinyML is also concerned with. And a lot of researchers have looked at algorithmic efficiency, things like quantization, pruning, compression of algorithms, and new types of hardware, SensMACH and work in the MEMS community and other kind of very exciting work that's marrying sensors with machine learning. I think we'll start to see more of these platforms coming out in the future. But what about imaging itself? What about the input data, the input sensing? How do we help reduce the power constraints at the sensing side? And it is a problem. Mobile devices have been limited by their battery life. For example, the Google Glass running continuous face detection, this was a couple of years ago, the study ran out of battery in 40 minutes, and 50% of that energy was in the sensing alone, just the image sensing and the transmitting of the image data to the computation unit. And you can't just rely on sending it to the cloud to do your processing. I think, I'm speaking to the choir here with TinyML folks, but, any kind of communication or readout is orders of magnitude more expensive than computation on device. And so we need solutions that reduce the energy for both image sensing and that communication of that data off the sensor. So the theme for this talk is, how do we utilize sensor programmability effectively in our algorithms and system design? How do we leverage and exploit the camera's different parameters to do this? And this is something that I have been using this term called software-defined imaging. It kind of has parallels to software-defined radio from the past couple decades, which the idea is that as the analog hardware gets more knobs and parameterizable and more open access knobs able for application developers, how do we leverage it for energy efficiency? So leveraging things like region of interest, selective region readout, exposure, quantization, and resolution for the energy efficiency of a vision system. So if you are familiar with the TinyML community, I gave a talk on this. You could go to the TinyML YouTube channel to see one branch of research where we were doing co-design of visual tracking algorithms with ROI subsampling. So this was a kind of predictive tracking algorithm where we're coupling object detection tracking with a kind of intelligence to help learn where is the object going to be in frame n+1 or the next frame. And we're pursuing both algorithmic solutions, but also FPGA implementations to see the benefits of this. And we have a bunch of work in RL and reinforcement learning algorithms to really get to like intelligent ROI subsampling. But in this talk, I want to talk a little bit about quantization and in the imaging pipeline. And the first work I'm going to talk about, this is a paper from ICCV 2017, was to look at the imaging pipeline. What happens from photons all the way to the end image that's passed to your machine learning algorithm? And it turns out that it goes through a camera pipeline that's typically can be made programmable. It's you know, a lot of machine vision cameras can adjust their settings on their ISPs and so on. And I'm going to talk about what an ISP is right here. An ISP, or image signal or image sensor processor, is the sequence of image processing operations that's applied to a camera's image to convert a raw image into a conventional image. So going through the optics and the Bayer pattern to demosaicing, white balancing, denoising, tone reproduction, there's actually like many more steps. This is kind of a simplified pipeline. So there's a lot of effort to make images look like a conventional image. This is maybe an example pipeline on the left here. And when your image comes right off the quantization of the sensor, it looks like this. It's dark, it's green, because the Bayer pattern has 2 green pixels for every red and blue. And so perceptually we see that. It's not been tone mapped, it's not been denoised, so on. So all of this work is meant to make images look aesthetically pleasing. But the question is, how much is needed for machine learning? How much do we need to do this for machine learning? Does a machine learning algorithm care if the image looks aesthetically pleasing or not? What steps can we remove or keep? So I'm just going to present some of the conclusions, the key takeaways we took from this study. First example is that if you're looking at quantization, there's a very fundamental rule of quantization, which is you want to use your bits most efficiently as possible, which means your bits you want to maximize their entropy, or you want to have the most information captured in the bits. So if it turns out light follows a log normal distribution, so it actually in natural scenes tends to cluster more in the dark regions, and there's less bright intensities coming into your camera than dark. But if we quantize uniformly, we waste a lot of the upper bits because they're not being used as much. And so to exploit this, we showed that log quantization is a smarter way to more efficiently code the information. And how do we test this? We took a bunch of different computer vision tasks: optical flow, stereo, structure from motion, stereo, and face recognition. And we showed that as we swept the number of bits down in the input images, log quantization did not explode in error as it did in linear quantization, as you can see in the first 2 graphs here. And there's actually an algorithm from coding theory and image processing called the Lloyd-Max algorithm, which basically minimizes the mean square error or basically designs an optimal non-uniform quantizer for a particular distribution. And with that, we were able to actually show that you can basically keep these flat curves for up to 4 to 3 bits on these things. So you're basically saving the energy savings from 8 bits to 3 bits, which is considerable. If you think about in the capacitor world, that's 1/2 CV squared. Think about how much less capacitance you have to do for SAR ADC if you only have to quantize 3 bits as opposed to 8 bits. So the conclusions from this study was that demosaicing and gamma compression were the most important stages for machine learning. Logarithmic quantization could help save energy while preserving vision performance. In fact, there's a very interesting insight that the logarithmic quantization is basically doing an effective scaling or tone mapping of the data to make it fit in the visual range that makes it look perceptible to us, but also is good for feature extraction. There's some other kind of interesting parts of this paper that I'm not going to go over here, where we actually designed a custom mixed signal circuit, just design, no implementation, to be able to approximate the most critical parts of the ISP pipeline, demosaicing and gamma compression, directly in the sensor itself. So that's an opportunity where your insights from your algorithms and how the sensor processing that goes into your input data can be baked into hardware for energy efficiency. So we want to take this one step forward, and this is going to be, I'm going to spend some time on this work, which is we wanted to analyze this for a particular use application, and that use application was Visual SLAM. So this is a paper that's going to actually be presented like in 2 weeks at the IEEE International Conference in Image Processing. And this is analyzing sensor quantization of raw images for Visual SLAM. This was work that partly Olivia Christie participated in the NSF SenSIP ROU program, so that's another workforce training program run by the SenSIP Center, and participated in undergrad research that led to this publication. So the motivation is, before I was talking about just general image sensing, but now I'm going to focus on the particular application of low power robotics, because that's a main application for the TinyML community. And particularly visual navigation via simultaneous localization and mapping. This is the algorithm where a robot tries to figure out where it is in the world and how far things away and features of interest and markers of interest are away from it. So it's both simultaneously finding where it is in a map and constructing the map at the same time. Now that's a very difficult problem, lots of visual processing requirements, but we need it to be working at real time without on the battery sensor so that our robots can stay deployed for longer. In our lab, we are focused on algorithmic solutions to make SLAM more energy efficient. And in particular, we're looking at how can we reduce the sensor processing for the input data. And then there's lots of work out there on making SLAM more energy efficient that is also can be coupled complementary to this approach. So what's the key insight? The key insight, again, is that images do not have to be aesthetically pleasing to be useful for low power SLAM, right? We're really interested in, can we take images like on the left and still be able to do SLAM without that loss of accuracy, or the trade-off between energy and performance for this. So again, we wanted to look at linear and logarithmic quantization of the raw images and see their effects with respect to accuracy of visual SLAM. And we also introduced a new type of quantization algorithm that's relatively easy to compute and helps improve performance based on gradients. So we looked at two different SLAM algorithms here. That these are two like very characteristic SLAM algorithms. We looked at, on the left, it's called LSD-SLAM. This is basically a intensity-based SLAM algorithm that uses pixel intensities to then estimate depth and camera pose directly. The other one, which is probably a slightly more common SLAM algorithm, is ORB-SLAM2. ORB-SLAM2 basically computes orb features, so that's a manual computer vision features, and then uses those features to triangulate the robot's location in the map and to compute the depth based on localization. And that's kind of like the classic SLAM algorithm, feature-based SLAM. So on the left is an intensity-based SLAM algorithm, on the right is a feature-based SLAM algorithm. And we want to see, does quantization affect both of these equally, or what is the differences? So again, we wanted to look at the ISP pipeline, and we wanted to figure out what we can do with raw images. So our pipeline, we actually use, and I didn't mention this in the ISP paper earlier, but we use a tool that transforms PNG images back to raw images with only 2% error that's been benchmarked by the creators of that tool. This was a paper from Kim et al. From Michael Brown's group. And so you take this picture on the left, and using the CRIP, you simulate what what its raw image would have been. Because right now there's not too many data sets of raw data for visual SLAM applications. And then we feed that through the visual SLAM, perhaps quantizing it or doing different types of ISP stages to see what the performance is. So we're interested in three types of quantization: linear, logarithmic, and gradient-based quantization, because this is what you might want to set your settings on the sensor when it's out doing a SLAM application. So linear and logarithmic quantization, I've already explained. Those set the levels based on a linear scale or a logarithmic scale. But gradient-based quantization is something new that we introduced. And the idea was, why waste bits on flat regions where there's not going to be that many features? Like if you have a plain flat sky, you don't want to quantize it with 8 bits necessarily. You could drop down to maybe 5, 4, 3 bits. So we came up with a way that encodes regions with high intensity gradient, and just measuring the gradient with very simple Sobel filters or convolutions, so it can be very low power, and quantize the lower gradient regions with lower bit values. And so we kind of just do a very simple algorithm to estimate the gradient in a location and then determine the bit value for that block. So what were the results of doing this? The first thing we looked at was logarithmic quantization. What we noticed is for ORB-SLAM on the right here, logarithmic quantization seems to work pretty well. Even up to 5 bits of logarithmic quantization, you've only suffered about 0.5 centimeter of accuracy in your map. So the map the most accurate is 1.70 centimeters of trajectory error of its localization, and then you only lose about half a centimeter, even going to 5 bits. Unfortunately, LSD-SLAM across the board did not work well with logarithmic quantization. As you see here, the errors are order of magnitude higher, order of magnitude higher than ORB-SLAM in the 50s and 40s range, and did not follow any consistent trend. The hypothesis is because that LSD-SLAM is not using features, but it's using intensity directly. And so if you do anything like logarithmic quantization, you're actually changing the distribution of intensity values. And that will cause a lot of the internal mechanisms of LSD-SLAM to break. If you look at linear quantization, what you can see is that ORB-SLAM 2, for linear quantization, starts to lose performance dramatically. It goes up from by quite a lot to up into the 20 centimeters, while you decrease the energy being consumed. And these are normalized numbers here. So there could be an effective trade-off point depending on your application and what you're comfortable in terms of error. However, with logarithmic quantization for ORB-SLAM 2, you can actually save like 88% of energy savings while keeping around the same level of AT performance using logarithmic quantization. So, one insight of this study, which kind of confirms our earlier research for a more general test, but particularly for ORB-SLAM, is that you can save energy by doing logarithmic quantization. We also studied, just very briefly, a little bit about resolution and frame rate. And here are the results, of course, decreasing the resolution of the sensor basically increased the ATE by a factor of 10. High resolution was needed to get accurate performance for the ATE. For frame rate, it didn't seem to matter as much. That's partly because ORB-SLAM is even working at a lower frame rate, but below a certain frame rate, the features just failed to track. And tracking is like one of the built-in parts of the feature tracking in the SLAM algorithm. So the main takeaway of our paper was that that novel gradient-based quantization algorithm we proposed actually was able to achieve an average bit level of 4.41. So look at this last column here. But its trajectory error was still under 2 centimeters of accuracy, and for ORB-SLAM 2. So it effectively saved about 3 to 4 bits of energy savings to get the same type of, same amount of average trajectory error, which is a considerable amount of energy savings. Now, as we noted, because we're changing the intensities, again, the LSD-SLAM had much more variable performance and did not follow the same trends as the feature-based methods. So kind of to conclude here is that it looked like the limitations that this method of looking at gradients and quantization only seemed to be beneficial for feature-based SLAM. And probably another type of sensor quantization schemes would be needed for intensity-based SLAM. The other thing we haven't done yet is tested on deep SLAM or these other neural network-based solutions that are starting to emerge. And it partly because they would be very difficult because you need to train on large amounts of raw data. And optimizing the algorithm for raw data for maximum energy efficiency could be an area of future work for vision pipelines. So in the conclusion, I just want to kind of, through my talk, kind of explain this idea of software-defined imaging is a way to exploit different mechanisms, ROIs, exposure, quantization, frame rate, to get energy efficiency. And to not forget about that when you're doing the total system optimization. And co-designing software and hardware, it's a great opportunity for the TinyML community. And there's a lot of interesting solutions in configurable pipelines, variable quantization, intelligent algorithms to, and feedback control systems for sensors. So I highly encourage anyone who's interested, you can visit my website there on the bottom if you want more information. And I wanted to thank the SensMACH community organizers for letting me speak today.
Again, thank you, Suren. That was excellent and some good work going on there for sure. If you have any questions for Suren, maybe I suggest you try and follow up offline, given that we're over time. I'd just like to thank all the speakers this morning for a great session. I'd like to thank all the attendees for joining in, and hopefully we can continue our dialogue offline, and obviously continue it tomorrow, where we start again at 10:30, and we've got some great talks coming up from NXP, the Quantum Lab at General Dynamics. We have Maxim Integrated, and we have my old stomping ground Intel Corporation speaking as well. So looking forward to a great morning tomorrow. Start at 10:30 Pacific time. And unless there's any questions, I think we'll call it a day. Thanks, everyone.
Thank you. Thank you, everyone.